Thank you. Good afternoon. Again, thank you for a very generous introduction. It's nice to be among friends because I have worked with many of you on many occasions, and I have voiced my views on these occasions as well. So I would just like to correct the introduction as well as Kalai Selvi. This is actually, I invited myself for this particular talk. In fact, I had spoken to Shekhar Mande before he retired, about a year ago, before he retired, saying that I would like to talk to CSIR scientists, especially in the chemical sector, trying to tell them is how they should think in terms of developing technologies. And I'll elaborate on this in detail during the course of this particular lecture. So I thought that this is a golden opportunity for me to put forward my views and opinions. Both may not be necessarily correct. You may beg to differ with me, and I would appreciate that, because as much as I'm a teacher, I'm still a student. So whenever I try to tell you something or teach you something, I'm very open to you pointing out a mistake in my presentation or in my argument, and I'd be more than happy to correct that particular mistake, rectify that. Because ultimately, the whole objective of this particular exercise is we learn together and grow as individuals, as a society, and as a nation. And we must exploit maximum possible capabilities of ourselves, and these capabilities needs to be identified first. I think I forgot my. So let us, my focus mainly because of my background is going to be chemical industry, but I will keep on referring to other industries as well, mainly because of my industrial connects. And fortunately, unfortunately, chemical project is one such project where only a chemical engineer cannot complete that project. A chemical engineer is supported by a mechanical engineer, a civil engineer, an instrumentation engineer. When I say brilliant engineers, mean they are not in a position to translate science into a technology. They have understanding of translating science into a technique, but to convert technique into technology, you have to have a financial angle to it. And that financial angle is somehow not handled at the beginning of the choice of the project. That gets handled only when you have a technique ready and you don't know what to do with that particular technique. And then you start searching for a product in the market, so on and so forth. So I'm going to talk about what is the correct methodology and modality which we need to follow. Something which I'm going to discuss about constructing a process synthesis tree based on whatever information which is available. What are the different types of plants which are existing in the chemical industry? What are the various phases of innovation? What are those technology readiness level? How the technology readiness level decides the quantum of funding which is required to take it to a next TRL level? And finally, what is the link between a technology readiness level and a commercial readiness level? Because many a times this is likely to happen, and I'll say that at an appropriate time during the presentation at that particular slide, when that slide appears, because otherwise we will be facing that particular issue multiple times. But let us wait for that particular slide. So the synergy between TRL and CRL, and if we follow that, we can be world leader. If you look at the typical, what they call it as Pasteur's quadrant, where you have 4 quadrants, something is fully applied, something is basic, something is totally applied, something is totally basic, something just publishes but doesn't get translated into a technology or a technique. And we are at this sort of a borderline somewhere. We are extremely good in terms of scientific publications, maybe 4th or 5th in the world. But as far as technological translation is concerned, we languish at about 45th in the case of ranking. And what is the way forward? So this is all details. I'm sure you have all these details. So government is pushing this with current 9.3% contribution to India's GDP, 7 to 9% depends. And government plans to have a total turnover of approximately $3,004 billion by year 2025. But which is that particular area which is going to allow you to increase this particular turnover? It is definitely not in the petrochemical sectors. It is going to be in the specialty chemical sectors, mainly because the kind of expertise in terms of chemical synthesis which exists in India is the one which needs to be exploited. If you are going to disrupt the existing value chain for the starting materials, such as maybe petrochemicals, the kind of investments which are required are so large that to disrupt the existing value chain or existing market scenario, the investments probably are 10 times our annual budget. So it is just not physically possible. Whereas with a fraction of this investment in the specialty chemicals, we can bring about the same value, because the economic value addition which you get from specialty chemicals is much, much larger as compared to economic value addition which you will get. Just to give you a simple example, you have a refinery. In the refinery, you produce fuel and you produce lubricating oil. Fuels are sold maybe 60, 70, 80, 100 rupees a liter. Lubricating oils are sold at 500 rupees a liter. Why it is that? Base is same. You add a certain specific additives to it, which gives it the tribological property, and it serves a specific function. The functionality of that allows you to charge. So if you look at any petroleum refinery, you will find that 80% of the profits of petroleum refinery comes from 3% volume, which is hydrocarbons used in the lubricating oil. Rest of the things, well, it also RAM category. And this is exactly what we need to exploit, because we have that particular expertise available, and I'll dwell upon it a bit more later on. So the specialty chemicals business as such is growing approximately 12 to 14% annually, which is about 2 to 2.5 times that of GDP. Now, this is a significant opportunity which is available to us. Polymers, agrochemicals present immense growth opportunities. Industries de-license except hazardous chemical. And I know I am also chairing Ministry of Environment, Forestry and Climate Change, Industry 3, the synthetic organic chemicals. So I know what sort of chemicals people are coming up and trying to put up factories. And you would not believe we are having meeting every 2 weeks for 2 days. In every meeting, we clear about 20 proposals without break. For the past 3 years, you consider 20 proposals being cleared or 40 proposals being cleared every month for 2 years, 24. So 240 to 300 new industries have coming up every year. Now, this is the opportunity. And why are they coming up? Mainly because they have market. They are actually showing that they can make money out of it and then sell it not only in India, but everywhere in the world. So the global shift towards Asia as the world's chemical manufacturing hub, I'm sure Prime Minister has multiple times told us that he wants to see India as a manufacturing hub. Chemical just happens to be one of the sectors. So these are typical areas where we have chemical sectors available. Agrochemicals, fertilizers, oil refineries, petrochemicals, dyes, dye intermediates, chloralkali, bulk drugs, paints, and inks. And I'll tell you Indian ingenuity. In 1970s, the European dye industry was completely destroyed by Indian dyestuff industries when they started making dyes. But when they were making dyes and dye intermediates, they did not bother about the environment, as a result of which the cost of manufacturing was significantly lower as compared to the cost of manufacturing of European industries. Over a period of 3 to 5 years, the European industries had to shut down their shops and they started importing the dyes and intermediates from Indian industries. And it peaked up. The China came along and China did exactly the same what we did to the European chemical industry. But China also realized that particular fact that this particular thing cannot go on forever. They cannot keep on abusing the environment. So they started tightening screws. Many industry had to shut down, and this is where the Indian ingenuity come into play. Indian environmental sector had also significantly tightened the screws. But when China started shutting down the factories, Indian business people went to China, purchased their second-hand equipments at throwaway prices, brought those equipments out there. Now you have reduced your capital investment significantly. You could afford to put effluent treatment plant, and now you started producing chemicals again. And now we are regained our earlier position as far as dyestuff industry is concerned. There is something to learn from this. See, one of the major problems in Indian scenario is capital is much more expensive. So we have to look into an opportunity where the capital intensive innovations are less, but intellectual innovations are significantly more, and we have that capability in India. So specialty chemicals, flavors, fragrance ingredients, and I'm sure CSIR labs have got presence in all of these specialty chemicals, right? Dyes and pigments, personal care active ingredients, water chemicals, construction chemicals, surfactant chemicals, textile chemicals, polymer additives, agrochemicals. Then why we are not having something like the Dows and DuPonts and the BASF type of presence in the whole world? One of the things which we are lacking is an excellent application center. We have the capability of synthesizing a chemical, but to translate that chemical and sell it to the outside world, we need to show its applicability. So we need to have an excellent application center, and that is where the European and US industries score, because they have got outstanding application centers. They are having a complete understanding of the structure property relationship of various molecules, and these molecules then are introduced into the market. And being a market leader, if you come as a second person to make it, your product is always likely to be compared with a product which has already been introduced into the market. And to be able to show your product is better, cheaper, you need to show that application center. Else, you need to offer significant economic incentives for them to buy it. And once it's like a human nature, when people are used to subsidies, you remove subsidies, people are going to agitate. Similarly, people start buying things with the subsidized product to capture the market. The moment you remove subsidies, they are going to agitate and start looking elsewhere. And I will dwell upon this in a bit more detail later on. So in the chemical industry, the basic problem is the time which is required to mature the technology. It has approximately 10 years as compared to, let's say, a software industry. 1 year, 2 years are more than enough. An engineering industry, maybe 4 or 5 years. But the stages in which the chemical industry goes, the maturity period is approximately 8 to 10 years. So we need to devise a method or a system by which you can crash this particular period. Those who have learned the technique of PERT and CPM, there is a process which is called as a crashing of the project. And this crashing of the project is done by allotting more resources to an activity where the activity can be speeded up. And you need to identify a critical activity, because if you are going to speed up activities which are non-critical, then it is not going to serve the purpose. So you need to identify which is the critical activity, and to identify that critical activity, understanding of TRL level in totality is absolutely essential. Because in a chemical industry, there are various technologies at play. Distillation is there, separation is there, purification is there, crystallization is there. And each of these technologies has got different levels of TRL. And the final overall technology of synthesizing that particular chemical gets decided by the lowest of the TRL level out of all those technologies which are currently operational in your chemical plant. And that's why identification of TRL level is important. So evaluation of technology maturity is, of course, understanding of the TRL level. So the original TRL level was done way back in 1974 by Stan Sadin for NASA. And there they wanted to predict what is the readiness level of launching a rocket, what are the different aspects which are there, and then this particular technology readiness level was translated to either chemical industries or engineering industries, so on and so forth. I have borrowed most of my presentations from two main papers. One paper appeared in Industrial Engineering and Chemistry, and second paper appeared in one of the UK journals. I will give the references of those which talks about TRL level as well as CRL level and the links between the two. But I will briefly going to describe all that sum up here. If anybody is interested in going a bit more detail, I will make those references available to you. So this is where the process synthesis tree occurs. Product identification. How do we identify a product? In the context of CSIR, what tends to happen is the following. Correct me if I am wrong. Scientists are selected based on their scientific capabilities. All brilliant scientists, no doubt about it. They continue to work trying to find out more and more science. And then somebody like Kalai Selvi comes and tells you, what is the use of this science? Show me where this science can be converted into technology. And then they start searching for a product based on the understanding of their chemistry. Somebody may be an expert in sulfonation, somebody may be in nitration, somebody in alkylation, somebody in esterification. And they tend to work in their area of expertise and try to come up with the product. And they propose a project, CSIR funds that particular project. But there is no confirmation of the fact that even if they produce that particular product, there will be a market for that particular product. And if there is a market for that particular product, what is the cost at which that particular product is going to be sold? What is the global market? Who are the other manufacturers? What are the quantities which they are making? What is the cost at which it is available? So on and so forth. So what is really required, and I was very pleased when I was discussing with the DG, that this thematic area with which you have started your activity is the activity in the right direction, where based on that particular theme, based on the need of an industry, based on the market. Now look at any funding agency. When you submit a techno-economic feasibility report to a funding agency, the person who is going to invest or the person who is going to fund, what is the first thing which he or she is going to look for? She is not going to look for the brilliant in technology, brilliance in chemistry. The first question that person is going to ask you, is there a market for your product? So the first thing which we need to identify is whatever you are trying to synthesize is and can be sold at a price. So what you do for that? Lot of literature is available. You need to do similar to doing a literature search for finding out multiple chemical reactions which can be used to synthesize a product. There are multiple routes which are available. You also need to find out from the market what particular chemical has a market, what has been the trend in the past 5 years, what has been the future for the past 5 years. Future is most important, mainly because unlike IT sectors or engineering sectors, maturity period is long. Your payback period in chemical industry can vary anywhere between 3 to 5 years. So unless you sell the product for 3 to 5 years at a pre-decided price, you will not be able to recover your investment. And recovering investment alone is not enough. You need to make money on that investment. So you need to see that the product is being sold at least for a period of 8 to 10 years. That is a typical life of a product or of a chemical. So unless you have a market for that duration in terms of quantity, it is going to be difficult for you to even think of synthesizing something. And then we will spend money, come up with the processes, make the product, but then we are stuck up with the product which is available, technique is available, but the technology is not going to be commercialized. And that is where the CRL level will come, and we'll talk about that. So we carry out a literature survey. Out of 4 or 5 routes, we choose one particular route. Why do we choose that route? Because that route gives me a possible product. The methodology, the chemists understand it very well. And then you do a preliminary economic analysis. What is this economic analysis involve? It just involves the cost of the raw material and the cost of the price of the final product. If the cost of the raw material is 50% or less than the final price of the product, then you can proceed ahead. If it is 60%, 70%, 80%, but if it's a one-step process, you may still consider it. But if it's a multi-step synthesis, then every time your yields are going to go on decreasing. So you can imagine you have 90% yield in every reaction, and there are, let's say, 5 steps which are involved, which is typically the case in case of pharmaceutical ingredients or APIs. So 0.9 into 0.9 into 0.9 into 0.9, you do it 5 times, and your product contribution from raw material comes out to be 50%. So these are some broad rules of thumbs which we can use at this stage and decide yes or no. And based on 4 or 5 different alternatives which we have, we choose that this is a chemistry which I am going to follow. So economic conclusion, if it is yes, then you move on and develop an input-output diagram. I'm going to refer to this particular diagram, process synthesis tree, in slides 10, 11, 12, 13, a bit more detail later on. Then we identify the sub-processes. That means what are the unit operations, unit processes which are being carried out to synthesize intermediates, convert that, purify that, separate that, so on and so forth. And what we do is develop a functional diagram. Functional diagram means a reaction, a separation, a purification. These are the functions which these specific units are supposed to carry out as a part of the entire chemical plant, which then gets converted into flow diagram with the material and energy balance. And then you have to make a choice of the equipment. When you say a choice of the equipment means you are going to use a distillation column. Should I be using a distillation column with the random packings, or should I be using distillation column with structured packing, which is going to be more expensive? The cost of the equipment will change. So you decide the choice of the equipment and you develop a flow sheet. Now, if you develop a flow sheet, once the flow sheet or P&ID, process and instrumentation diagram, is ready, again you have to assess the economic valuation. Now, if you find that in the initial stages, on the basis of chemistry, it was economically viable, but now it is becoming uneconomical. If there are 2 options which are there, there could be a third option as well. If it is no, the answer to it is no, then you go back to the chemistry and see how the chemistry can be tweaked. If the answer is yes, or there could be answer of maybe. If the answer is yes, then it becomes a candidate. If the answer is maybe, then the line is missing or a diagram or an arrow is missing out here. You need to go back to the specific choice of the equipment. Because till you made the choice of the equipment, the synthesis tree was showing viable economics, but because you made a choice of the equipment, it is now rendering capital intensive and it is now rendering maybe category. How can I rectify that? Can I use second-hand equipments? Can I combine 2 or 3 operations into a single equipment and reduce it to make this particular process economically viable again? So there are yes, no, or maybe, and then we need to sort of reiterate till we identify a candidate process, which is now for us to take it forward. This is a very busy slide. Don't bother to read it, but I'm just going to explain in brief what is going to be there. Please tell me the time this thing. Because I get carried away. So we have a laboratory. So typical tasks which we carry out in the laboratory. In the future characteristics elements. Analysis, basic kinetic studies, thermodynamic studies, analysis of thermodynamic properties. Many a times what happens is, you know the chemistry, you can handle that particular chemistry on a lab scale very easily. But when it comes to scale up version, engineering properties which are required, physicochemical properties of the chemicals which are required for engineering design of the equipments are many a times are not available. So you need to study those properties at the operating temperature and pressure conditions, and that is very expensive proposition. Many of the software tools are available based on the group contribution theory, so on and so forth, but you cannot be investing 1 crore of rupees based on the calculations done on the group contribution theories unless you have 2 or 3 real data confirming that your group contribution method is correct and predicting the properties properly. And this is very expensive proposition. So what you try to do is you have multiple points in the process elements which are there, you connect it and put it in the form of a mini plant. It is not a pilot plant, it is not necessarily a lab plant, but it is a mini plant. Doesn't have to be continuous, but it still sticks to the time schedule. I'll give you a simple example. We developed an herbicide for Godrej Industries Limited. At a 1 kg level, everything worked out beautiful. The product showed 97% purity, had an excellent functionality as a herbicide, and we decided to scale it up to 1 ton, from 5 kgs to 1 ton. The only difference in that was there was a process of filtration. In case of a lab, that 1 kg mass, 5 liters of mass could be filtered in about 10 minutes. Whereas in case of 1 ton, approximately 3,000 liters of mass could be filtered over a period of 3 hours. Now the product was remaining in that filtrate for 3 hours as against 10 minutes. And we realized that keeping that product in that particular atmosphere for 3 hours was degrading the product. So these kind of analysis needs to be carried out before you do the scale up. So we had to stabilize that particular product by adjusting the pH before we could carry out that filtration. And then the process was standardized. And then now the product is available in the market. The point which I'm trying to make is this a difference between the mini plant. Mini plant tells you what are the specific functions, and you need to find out the time required for those functions and whether these times can be compromised when you scale it up or they need to be matched exactly as per the mini plant is concerned. Then you have a pilot plant where you require significantly higher levels of investment. I'll talk about TRL level and the investment levels which we talked. And then we have a demo plant, general proof that the technology is suitable for the targeted economic purposes. And this is where actually at pilot stage itself, the CRL makes an entry. Right, till that time, CRL has no significance, as we will see in due course of time. Then it is a question of integration, and you will always find that every new plant which comes out doesn't produce 100% of its rated capacity in the first year. It produces maybe 60%, 70%, but there are plants which will produce 120% and 30% and 40% of its capacity as the technology matures. Now, the simple reason for that is you have not done the design from the first principles everywhere. You have used empiricism, and that empiricism allows you to exploit. You give me any plant which is designed in, let's say, 70s and 80s, and let me have a look at it, and I guarantee I will give at least a 30% enhancement in that particular plant with minimal investment. I was consultant to Godrej Industries Limited, make fatty alcohols, had a plant capacity of 70,000 tons per annum. With an investment of few thousand, we could take up that capacity to 140,000, double the capacity. Now that, of course, is going to make the product economically much viable. It is going to make you a market leader, but this kind of analysis is required. So let's move on and move to our TRL level. Basic research doesn't include the TRL. It's what we call it as a blue sky research, exploratory research. And many of the scientists who are selected in the CSIR set or CSIR systems have outstanding capabilities in this particular direction. I think they are brilliant. I have absolutely no complaint about their scientific capabilities at all. None whatsoever. Then it comes to applied research. Now it is a basic question mark out there. What tends to happen is scientists usually don't like to be told what to do. Right? This is where the basic problem arises. They feel that they are independent free birds. Now that is only true in case of people like us in academics, where nobody dictates, you must work on this area, you must work on this area. I don't want to work. I do my teaching. Don't ask me to what I need to work on. But in the setup like CSIR, you have a responsibility towards both. You're partly academic, you're partly industries. So you must be in a position to at least compromise your time, partly for basic research and partly for applied research. And I say that even in case of academics, every academic should at least spend 15-20% of its time in identifying socially relevant problems using the same technique, technology, or engineering skills which you have learned. And these engineering skills can then be applied. You develop technologies which will benefit industry by all means. Earn your money through that, through consultancy, no problems at all. But at least have some, let's say, responsible feeling. Government has spent huge amounts of money on your education. When I did my BTech from IIT, my annual fee was 420 rupees, 120 rupees for 12 months of hostel, 300 rupees for tuition fees. And I completed my education in terms of 5 years of integrated BTech with fees being paid 420 rupees. Now, if I don't own this responsibility and contribute to the industry, what is the purpose of my education? Not acceptable. You have to be in a position to give some time as a national responsibility to come up with socially relevant problems and use your engineering and technological skills to find such social problems. We get time, I'll tell you some of these products which we have developed in ICT. So you have applied research, then the development describes the conversion of research into creation of new and improved products and processes. Improved products and processes can be in terms of kinetics, in terms of materials, in terms of utilities, so on and so forth. Right? Multiple options of optimizations are available and cost reductions are available. As per Professor Sharma's favorite saying, no technology is ever mature. Technology always continues to improve till it reaches its thermodynamic limit. You can't beat thermodynamics. Right? Once you reach second law of thermodynamics, you can't beyond that, you can't cross that, but at least you should make an attempt to reach it. And one of the technologies which is almost reaching that is the technology of ammonia synthesis. Ammonia synthesis is nearly there, not still quite, but nearly there, but it still gives you an opportunity or energy integration, process integration, which is still possible. Then this is what we call it as applied research and development in terms of the general parlance of industry. And then bringing the development technology into effective action mode, and this is what we call it as a deployment of technology. And as you can see from here, basic research does not have a TRL level, 1, 2, 3, sometimes 4, and as correctly pointed out by the DG, that CSIR tends to support 1, 2, 3, 4 and develop the essential TRL level 3 and 4. After that, it is absolutely essential to get an involvement of the final person who's going to synthesize that, make that, market that. Without that, there is not an iota of chance that this technology will be taken up later on. And I'm sure there are examples from CSIR labs at IICT, NCL, CSMCRI, where these technological arguments, after reaching a TRL level of 3 or 4, have been reached and has resulted into a final sellable products. And then there is deployment. Now, deployment, of course, is based on the industrial input. The investors are there. But for those investors to be able to invest the kind of money which is going to be required to have a full scale or a large scale plants, it is necessary for us to understand the commercial readiness level. Technology can be developed, it is making money, but what is going to happen is there is a concept which is called as EVA analysis, which is called as economic value addition. Let us say I've got a lakh of rupees to invest. How do you invest? Do you just go and make a fixed deposit and invest it? No. What you do is look at the mutual market, look at the share market, look at FDs, and see which particular investment is going to give you higher economic value addition, and you invest into that. So assessment of commercial readiness level doesn't only involve the commercial viability, it also should involve the economic value addition to the technology which you are trying to sell. And that is where the maturity of the technology in terms of commercial readiness level will come into play. And then that is the deployment. So these are again very busy slides, but this is essentially pointing out to the same facts which were there in the original process synthesis tree or the process synthesis framework which I had talked about. Ideas, opportunities identified, I have already spoken. How the ideas need to be identified based on the market need, based on the requirement of a product. Then the concept, what are the patents which are already available, market survey, the price of the product which is being sold, the percentage contribution of various elements in that particular product, what is the raw material cost, what is the utilities cost, labor cost, etc., etc., etc. They need to be added, and you work out the proof of concept based on the laboratory research. So this is what we call it as a basic engineering package. That basic engineering package you should be in a position to make after you have reached a TRL 3 or TRL 4 level. Only on that basic engineering package research you will be able to market it and sell that particular idea to a prospective industrial environment. Then we carry out detailed process development where we convert the basic engineering package into a detailed engineering package, which is a very expensive activity, and I'll relate the extent of investments and the money which is required as compared to the TRL level. You got to demonstrate the full-scale engineering, then commissioning, and finally the production. Now, all of this has got multiple bottlenecks available. What are those bottlenecks? Only when you look at specific case studies, and if you are keen to have a look at our business case studies, our business school magazines, you will find umpteen number of case studies available, especially in terms of business. They won't talk about the technological readiness level, but they definitely talk about commercial readiness level, which you can utilize. Then you have project criteria. See, general project criteria, which is related to the input-output diagram, which I talked about in the case of process synthesis tree. So there's a tangible work result, the workplace where you carry it out, and what is the outcome, what is the deliverables at that. In terms of ideas, rough concept, vision, strategy paper. Usually this is all based on paperwork. Then you have concept, technological solutions, could be numerical solutions, could be Aspen-based solutions. Fair enough, doesn't matter, but you should have that solution readily available, which then can be converted into a proof of concept, and you can assign certain values to it. You can use certain weightages to it, and this weightage selection is also equally important when you make a choice of the chemistry. And I think even in India, the anti-dumping duty is only applied when you convincingly show that the final cost of the product is less than the cost of the raw materials which is available in the international market. Only when you show it to the industry, to the government will consider thinking of anti-dumping duty. Till that time, government will allow the import of that particular chemical without any anti-dumping duty. And anti-dumping duty is, of course, managed essentially taking into account these differences which occur. Then detailed process development, I've already talked about. They are either in the form of laboratory or mini plant, and the product properties. Now, this is where, again, the application center comes into picture. Application activities. If you synthesize it in the lab and sell it out and give it as samples, it works. You synthesize it on a larger scale. There is some small element which is missing, which you don't identify, but it doesn't give the same function which is available or which is supposed to give. We did something. We developed some called a single atom catalyst. It worked beautifully. Then they said that you synthesize it on a slightly larger scale. We want to try it out on our pilot scale. We tried to synthesize it in a lab, a larger quantity. Catalyst not showing any activity at all. On a scale of gram, it was showing excellent activity. The moment milligram, it was showing excellent activity. The moment we shifted it to gram level, no activity. Now, these are the bottlenecks which you are going to encounter, and we need to develop strategies to handle these particular bottlenecks. And this is a part of the technological developmental activity. Technique to technology involves specifically scaling up and assign value to each of these activities. Pilot trials, demonstration and full-scale engineering, commissioning, final system, product side, product customer acceptance, so on and so forth. This is again involves a lot of marketing efforts. See, this is one of the reasons why you would find that when the scale of operation is small, technologists are the drivers of an entrepreneurship activity. When the turnover increases beyond, let's say, 100 crores, 150 crores, marketing people will start playing a more dominant role, because they know that if the industry has to grow, we need to sell more product. So we are the kings, so we must demand more product from the industry. Once the turnover crosses about 500 to 600 crore, the finance people don't care a hoot, right? Neither to technology developers, not to marketing people. Only the finance people do it, because the kind of financial jugglery which they do, they are able to earn much more on that investment as compared to any of the technologists or marketing people. You all have experienced it. In all the cases, where does the buck stop? The buck stops with the finance department. Everything gets cleared, technology gets cleared, but it gets stuck in the finance department. But this is a universal rule. We must accept that particular rule and be ready that you got to make it financially so attractive. And that is what the disruptive technologies is all about. Now, to come up with these disruptive technologies, it is not only synthesis of a product or synthesis of a chemical is important, it is equally important. It is equally important for us to look at the costs associated with it and the kind of cost benefits which you are going to get. And that is the only language the finance people understand. You show me an increase in the bottom line at the end of the year, fine, done. money given. Again, these are all details, reaction engineering ideas. See, many of these complex synthetic organic chemistry based reactions are very difficult to analyze from kinetics point of view. Not impossible, but the number of experiments which need to be carried out are very, very difficult. And this is where the new concept of digital twin comes into play. You don't necessarily have to carry out experiments to understand the kinetics. You can use a data-based approach. You carry out multiple experiments on a smaller scale, little variations in the parameters which you are likely to have, generate a lot of data, and let the AI or ML crunch that particular data and come up with a model which is statistically significant, scientifically rubbish. You don't worry about it. Ultimately, what is your objective? Your objective is the system should work at an enhanced scale. And these models are likely to work, and they do work once you are in a position to have sufficient number of data sets. And that's why AI ML is going to rule the world, mainly because you look at any refinery. The refinery have got 50, 60, 70 years of data. They don't know what to do with that particular data. Similarly, our government is insisting that every effluent treatment plant, every boiler should have an online monitoring system of emissions, online monitoring system of COD, BOD. Who's doing what with that data? I have absolutely no clue. If you use that data, analyze that data, and come up with the policies which are based on that data, then people will also feel confident that yes, they are contributing to that particular data, which is deciding the final policy. So it is important for us to also consider that. So proof of concept, preliminary process development, feasibility of the reaction, kinetic data, pilot trials. This is again various stages. How these stages are important in the overall process synthesis tree development, which I talked about. I had only sort of a box and blocks out there. Each of these slides essentially tell me about details of those blocks and what we really need to carry out. Process system engineering is another important, mainly because you're integrating multiple activities in the final process plant. It is necessary for us to have the processes which are accounted for, the interlinkages and interrelationship between the various processes. Again, unit operations, combining unit operations, whether cost can be reduced by having multiple, can I have a filter cum dryer? Can I have a reactive distillation? Right, a simple reactive distillation, one column can synthesize esterification based reactions like acetate, butyrate, so on and so forth, as against 6, 7 columns which used to operate earlier. So such type of technology, disruptive technologies are available, are being developed. And that's why I said no process is ever mature. The processes are likely to get developed continuously. So the final flow diagram, again, concept, preliminary economics, preliminary process development, economics based on sub-processes, detailed process development, process flow diagram, P&ID, where you have Aspen, optimization, ANSYS, CFD simulations available. You can use all these techniques available. It's not necessary for you to actually do the experiments. Numerical experiments are equally strong, equally predictable, and equally accepted. Then you have pilot plant trials, enhanced processes, again, economic based on the choices of the equipment. Then you have a candidate process. And as I said, most of these designs, if they're empirical in nature, over a period, as the technology matures, you would be in a position to get at least 30% enhancement in the productivity of these chemicals. So these are the typical recommendations which are made in terms of your thinking in terms of commodity chemicals, pseudo-commodity chemicals, fine chemicals, and specialty chemicals. Right? These are the tons per annum, and at various scales of operation, what are the typical scales at which they need to be carried out so that with a confidence you can scale it up to different sizes and to get full scale production. So at proof of concept level at what scale, preliminary process development at what scale, detailed process development, pilot, demonstration, commissioning, and product. depending upon the type of chemical which you have identified, whether it fits into a commodity chemical or pseudo commodity chemical, a fine chemical or a specialty chemicals. Boundaries are not rigid. The boundaries can go here and there. And you see the kind of development which happens in pharmaceutical industry, which is really exploiting. But pharmaceutical industry has got a different model. What do? They don't identify new molecule, because identifying new molecule going through phase 1, phase 2, phase 3 trials is extremely difficult. So what they do, they look out for the patents which are going to go off after 20 years, identify those patents, look at the processes, tweak the patents so that they can put a drug master file, claim their patents, and the moment patent comes off the line, they start producing it. But here also, in the hurry of filing a DMF or a drug master file, many of these processes are sub-optimized. And then they realize it, I could have done this much better, but it is too much of an effort to change the DMF again and get it. By that time, the generic has already gone into the market, they are already being sold. So once you start getting money, people sit, they don't necessarily want to improve. Right. So these are some of the examples which I have given in terms of TRL. I'm going to skip both these slides, and this thing is available to you. You can use it. So in case of, if you say separation is the idea, then I have distillation, rectification column, tray column, and you look at the TRL levels of each of these. What is the knowledge base which is available to us? What is the theoretical models which are available to us, on the basis of which we can do a confident design and confident deployment? Similarly, if I extend this further and take a case study, you look at the various stages of the manufacturing activity, a continuous hydroformylation, and you will find that at different stages are at different TRL level. But as far as the overall hydroformylation and the formation of the product is concerned, it is at only TRL 4, the minimum or the lowest TRL level among all the activities which are present in there. And that's the most important thing to understand. It's like identifying a rate controlling step in your chemical synthesis process. If it's a 5-step reaction, one of the steps is slowest step, then that is the step which needs to be worked upon to speed up that particular step. So what is CRL, right? So commercial readiness level assesses the product's commercial maturity on a scale 1 to 6. TRL was 1 to 9, 1 to 10. Initially started with 7, then the 2 scales were added later on. Starts at CRL 1 when the commercial potential first emerges, right? That means, yes, it appears that this particular product has a commercial value. The commercial readiness level, like TRL, is critical for determining and measuring organizational maturity, right? What do you mean by organizational maturity? You have a technique available, you have a technology available, but am I, as an organization, have the capability of exploiting that particular technology? Do I have the marketing skill set? Right? This concept arose as a supplement to TRL because it became clear that technological maturity alone does not ensure the success of products and enterprise. This is like go to a hospital, talk to the surgeon. Surgeon comes out of the operating theater and says, operation was successful, but the patient died. So essentially, it doesn't serve a purpose. And I have experienced it myself. I was associated with one of the processes when I was in England, and this process was mycoprotein. Mycoprotein is essentially a protein which is of vegetable origin, where the substrate is methanol, and the microbes are a fungal type, and the fungal density increases, and then essentially you get strips of protein, right? Completely vegetarian in nature, because it's a fungi which is being eaten like a mushroom. But this was far ahead of their time. At that time, a 40-meter cube reactor pilot plant was successfully operated, but commercially the entire activity failed. Now, This was, I'm talking about 1984, 85, 87. Now, after a gap of nearly 40 years, this particular technology is coming into it with the availability of vegetarian meat or synthetic meat getting popularity. So that particular product was ahead of its time. So it was technically brilliant, but commercially not successful. And that is why assessing commercial readiness level is equally important for you to assess the deployability of that particular technology. Right? So hypothetical commercial proposition driven by technology advocates with little or no evidence of veritable technical or financial data to substantiate claims. Yes, we can possibly do it. No data is available, but on back of the envelope calculations or with some calculations, you can say that if I'm able to make this particular product at this rate, I can sell this, I can have so much of product, so on and so forth. Then we carry out a small scale trial, first of a kind project funded by equity and government. This is where CSIR funding can come into that. And this will start only when you have reached a TRL level 6. CRL level 1 starts when you have reached TRL level 6, not till then, right? Then commercial scale-up occurring driven by specific policy and emerging debt finance, where the commercial viability rather than technological viability is a selection criteria in terms of taking this particular project further or curtailing this project. Here is that, okay, fine, you have developed a technology. This technology does not have any value as of today. We will keep this particular technology in hibernation. When the market is ready, as in the case of mycoprotein, we'll bring out this particular technology again. Unfortunately, it could not be done by ICI because ICI itself is partly closed. It has shut down its operations. The plant was sold to somebody else. But Chinese companies and one Brazilian company are coming up with this particular using the same old technology. Then market competition driving widespread deployment in the context of long-term policy settings, competition emerging across all areas of supply chain with commoditization of key components and financial product occurring. And then you have bankable grade assets, class driven by same criteria as other mature energy technologies. Now, that's why when they say that we want to get into renewable energies, develop renewable energies, we want to have hydrogen as a fuel, long way off, right? Yes, making effort in that direction is indeed, but saying that in 3 years' time we will have a technology available, it will start penetrating, is we are in fool's paradise. Don't even think of that. That is not going to happen. But that doesn't mean the effort should be stopped. But the effort should be focused. See, spending money smartly is more important rather than spending money fast, right? Even if you don't spend money, but spend money where it needs to be spent, that money will give you much higher return, much higher EVA as compared to spending money for the sake of spending money. So this is where it starts, right? TRL2, CRL1, technically and economically untested, unproven. When TRL7 or between 6 and 7, CRL level 2, commercial trials of technology on a small scale. CRL3, commercial scale up of the technology means what? You're making the same product, the product is meeting the same specifications as on the smaller scale, and the market is accepting your product. Then CRL4, multiple locations at which are similar, not only one plant, but 2 plants, 3 plants, 4 plants. And that is what will give a confidence to the investor that he or she is not the first investor. Now, this is a typical question which is always asked by an industry. When you suggest a new innovation to them, the first question which the Indian entrepreneur asks, when I say, I shouldn't say entrepreneur, but industrialist, is, "Pehle kisne kiya hai?" They are afraid to try something new, right? They don't want to be guinea pigs. Now, this mentality has to change if Indians are going to get into innovative solutions for making of chemicals. But it is up to us to convince them, right? किसी ने किया नहीं होगा, but theoretically you look at it. I'm proving it on the basis of paper. Doing these theoretical calculations, you show it to best scientists in the world. Let them validate those and come out with a mistake. If the mistake is there, I will not say it. And this is what the scientist's responsibility is. Whenever they are offering innovative or solutions for the first time, it is his or her responsibility to convince the person who's going to implement or employ that particular technology or the suggestions. Then CRL5, market competition, industrial acceptance, driving by widespread application, and readily financial support of technology by bank. That is CRL6. Meaning what? You come up with that particular technology, go to a bank, and bank will say, oh, you are using this particular technology supplied by UOP? Yes, yes, we are willing to fund this particular activity. That is the commercial readiness level 7, where you can say now that this technology, I can sell it anywhere in the world. So the technology readiness level and commercial readiness level go hand in hand, but at various stages. There is one particular slide which is missing. I don't know why. There's a figure out there. It essentially was showing the following. I don't know why it is not being seen. But what it shows that the technology readiness level up to TRL 3 or 4, about 4 to 5% of the overall project cost needs to be spent. 4 to 5% of the overall project cost. From technology 4 to 7, you need to spend almost 40 to 50% of the overall project cost. And that is what we call it as a valley of death. Majority of the technologies are successful TRL 4, and because they have not been commercially assessed in the right format at the right stage, they don't get any support. And they don't get any support, obviously, they can't proceed from TRL 4 to TRL 7, 8, where the industry is willing to invest into it. So that particular graph which showed, and this assessment of technological readiness level and the investment, these are the numbers which I am telling you, typically 4 to 5% up to TRL 4, 5 to 50% depending upon the type of technology, to translate it from TRL 4 to TRL 7, TRL 6 or TRL 7, and then the balance 50% you would require for implementation of a full-scale technology. Even if you keep these particular numbers, as far as the funding from CSIR for fund these projects are concerned, when you are especially have assessed that this is technology at TRL 4 level, you can't be supporting all the technologies to translate it from TRL 4 to TRL 6, 7. You need to do EVA analysis of this technology. Meaning, if I'm going to invest 2 crores of rupees on this particular technology, and if the technology is taken to TRL 6, 7 level, can the spending of 2 crores of rupees by CSIR is going to result into technology which will give me an annual revenue of 20 crores when the technology is matured 10 times, order of magnitude. And out of 10 TRL 4 technology, you select 1 or 2 or 3 at the most, depending upon your budget. And you support those that will ensure the funding available for the right technologies which are at a commercial break-even level, and the kind of revenue which the CSIR will able to get. EVA analysis, economic value addition. If you are investing 2 crores from TRL 4 to TRL 6, you must expect a return of at least 10 crores, right, or 20 crores, 10 times. If that is your criteria, you will have a project assessment done by professionals. And you people have the capability to do this activity. So if you combine TRLs and CRL, the synergy, it is accelerated time to the market. It reduces the risk mitigation, efficient resource allocation. The one which I just mentioned is you have limited resources and you're allocating resources, which gives you a maximum EVA, maximum economic value addition. It also going to foster innovation because people will start thinking right from the beginning that they are not just innovating it, they are innovating is essentially to earn money. Jugaad is fine, but that Jugaad needs to be scaled up. It is translatable and it can be implemented or deployed at multiple locations. So it becomes now a customer-centric approach rather than a scientist-centric approach, which currently is existing in CSIR. It should be a customer-centric approach. And the customers are who? Customer is our nation. A nation is your customer. And whatever are the needs of the customer, you must service the needs of these customers. So what is the way forward? To further strengthen the discussion about TRLs and CRLs in chemical industry, a lot more work can be done. There are excellent reports, articles available on both these particular aspects. To encourage application and adaptation of these presented scales, additional criteria and TRL, CRL level can be arrived at depending upon your own experience. It's like when the original 7-level TRL was being adopted for chemical industry, they found that this is not enough. You need to have additional 2-3 TRLs added to it, as a result of which they came up to TRL 9, TRL 10. Safety engineering, every activity needs to be assessed in terms of safety, not only economic EVA, but EVA at what cost also needs to be looked into, whether it is at the cost of environment, whether it is at the cost of green cover. All these things need to be looked at. Project characteristics, what are the people, institutions which are involved, guidance on how to derive a maturation plan for R&D, and D means deployment, research and development and deployment tasks which you are going to carry out. And adaptation of scale of different purposes, readiness for ecologically sustainable production. One last point which I'll make in a minute and then I'll stop. Any of the large scale mega projects, which are essentially, we call it as a big ticket project, should involve some social scientists, not only engineering or basic scientists. Mainly because the basic scientists decide that this is the product which the society needs. I can decide that this is the product they definitely need. And when they develop a product and they go to the society says, who asked you to develop this product? I'm not interested in this product. As a result of which all the efforts are completely lost. Right? Most of the US and UK or European funding agency, when they are sponsoring projects, along with the PI, which could be an expert in that particular scientific field, they also have marketing people and they also have social scientists assessing every activity during the project developmental stage and checking whether the outcome of this particular activity is going to be socially acceptable or not. If it is not acceptable, they will stop from wasting time, wasting resources, wasting money in conducting that particular activity because it is not part of the project. The deliverables doesn't include exploratory science or a blue sky research. It expects you to deliver, which is a socially acceptable process or a product. I think I'm going to stop here and thank you very much for your patient listening. And if I've exceeded my time, my apologies to you, but this is where I'll be more than happy to answer any queries, questions which you may have. Thank you. Please.
Please take care of the
Hello, sir. Yeah, fantastic talk. So, in short, do you suggest that CSR should be involved or not to be involved in basic research only?
Nothing of the sort. If you want a sustainability for CSR, they must spend money, time on basic research. It is just a question of orienting the brilliant scientific minds which are there in CSR, that their job is not only doing the basic research, but out of 10 exploratory ideas which they are working on, at least think of one or two ideas which also have a commercial viability.
So, yeah. And second question is that, like you told TRL 1 to TRL 10, and how many steps of TRL level CSR can cross at this moment, or do you expect to cross from bottom to top or up to certain level and then bring partners, something like that, or all together from
No,
1
I
to
think
10?
as far as CSI's budget is concerned, CSR does not have the wherewithal or the budget to support technology from TRL 1 to TRL 10. No, sorry. Majority of the support should come to support activities which are up to TRL 4, and maybe one or two activities which are desperately needed or activities where are the nation's priority can then be utilized till to TRL 10 level. But even then, once you reach TRL 5 or 6, involvement of an industry or implementer is a must, because CSR is not or does not have a wherewithal to run a commercial entity and market those particular technologies the way you expect those technologies to generate revenues. Thank you. Yeah, Vibha.
So very, very thought-provoking talk, I must say.
Thank you.
Thank you so much for it. Just one question to you. When you say commercial viability, is it the same as the economic viability, or is there any difference between the two?
No, economic viability gets only on the basis of market which is there, market price of the product which is there, and what is your manufacturing cost. By the time the market reaches a customer, there is at least 2 times increase in the cost. So if you are going to make something like clay for 50 rupees a kg, by the time it reaches a customer, it is being 100 rupees a kg. You have a distributors which will get their pound of flesh about 15%. Otherwise, they say my effort for getting 5% return is not going to be enough. You give me 15%. Then they are stockists. They will extract their 15%. And by the time they take it from the manufacturer will get only 50%. So at 50% level of the product cost, and you sell it at that particular cost, it would have made you at least 20% return. So your product cost in terms of the final product cost and you being able to run an enterprise successfully and sustainably, you have to think in terms of 30 to 40% of the final product price which is there. This is in terms of economic viability, and this is all on a piece of paper. Commercial viability comes that you have an invoice and an order available from your prospective customer for the next 3 years, next 5 years, next 10 years, at least till you recover your investment and start making money on your investment. So commercial viability adds the marketing capability, market availability, and market level of maturity of the product as compared to only economic viability.
So economic viability is a kind of a prerequisite to anything becoming commercially viable?
Absolutely. Unless government says that, like Covaxin or vaccine, You make it irrespective, whatever is over your manufacturing cost, we will support that particular cost. And then that doesn't become a commercial viability. Commercial viability, it becomes because you got an order from the government of 2 million doses, 10 million doses, at 100 million doses, which are there, which is going to ensure that whatever investments in terms of vaccine manufacturing you have invested is going to pay back.
Okay. Right. Thank you.
Sir, very nice lecture.
Thank you.
We really liked it. My question is that
You're not saying it just for the sake of saying it, no?
no. I really mean it.
Because you know me, that's what I'm saying.
No, I really mean it, sir. My question is that you suggested, you presented that the CRL, commercial readiness level, start somewhere around TRL 6.
Yes.
So if we have to go through TRL 1 to TRL 6 and then do the CRL and find that CRL is not feasible, then what happens to the investment on TRL 1 to 6?
Very true. But that is what I'm saying, that TRL 4 to TRL 6, you will not be doing it on your own. You will be doing it in conjunction with an industry. You will not be spending all that money on your own. You have already spent money to bring it to TRL 4. TRL 4 to TRL 6, which is approximately 5 to 50%. Significant amount of money should come from industry. Then only it is worthwhile for you to proceed. Otherwise, no. Unless you identify one or two technologies which are really, let's say, disruptive technologies, where you know that nothing of the sort is available and will be made available in the next 5 years or 10 years. And if I come out with this particular process for the product which I'm making, I'll be able to sell this product sustainability at the required profit margin for the next 10 years. Then only. But I don't think we have that, let's say, skill set existing in CSIR. Maybe you can get some outside experts and outside help, consultants to do that. Because our Srinivasan of CSIR was asking me, sir, suggest a consultant who will really assess the commercial readiness level. Not available. I tried so much. Right? There are no commercial entities, and the only commercial entities which are available are the R&D people from industry and how they are directed to spend money on development of technologies. What industry is doing? Industry has seen the market. It has seen the market trend. It knows that 5 years down the line, which particular chemical is going to be in demand. For how long? Now they will go back and tell their R&Ds, research and development, now you develop a technology to make it at this cost. A typical model which is followed by Unilever is let's say they decide to come out with a new soap. What they will do is new soap is synthesized, new fragrance or new color, new shape or whatever it is. Then they will have an internal committee within the Unilever enterprise itself. And then they will distribute this particular soap and ask their opinion in terms of how is the quality of the soap, so on and so forth. Let's say the soap is of 70 grams. An equivalent soap is available for 15 rupees. How much more will you be willing to pay for this special soap? And they will get some number, maybe 2 rupees more. So 17 rupees, 18 rupees. Fair enough. So there is a potential. If they say that I don't want to pay anything extra for this soap, existing soap is good enough, they will drop that idea. But if somebody says that, yes, I'm willing to pay 3 rupees more for this particular soap, then they'll make a slightly larger batch and go out of Unilever and do a market survey. And again do that. And they say, no, we will pay 2 rupees more maximum. So from 3 rupees margin to 2 rupees. So now you got to make a soap in 17 rupees. Now to make a soap in 17 rupees and sell it to the customer in 17 rupees, taking at the cuts of distributors, stockists, so on and so forth, I must be making that soap at 8 rupees. Now they will go back to the R&D and tell you make this soap in 8 rupees. That's your mandate. And that is how R&D works. So similar R&D kind of an activity needs to be carried out for some projects, because CSIR is not an industrial R&D center. Right.
That's what I was thinking, that if we are putting so much condition, we will be left with very few projects, and that everything may not be feasible for CSIR.
No. Everything need not be feasible. But Pandey Sahab, what you should do is identify one or two projects which are high EVA projects. So, एक CSIR technology बाहर दे दिया, the kind of revenue it will generate, PM will say, forget, you earn whatever you want to earn, spend whatever you want to spend, you have made yourself self-sufficient.
Okay. Thank you, sir. Thank you.
Thank you. Yeah.
This is Dr. AMRIT Sorakia. Now, because you have said that not to appreciate your lecture, so in the lighter vein, ki sote se utha diya. Your lecture has cemented one of my thought, that there is a big difference between R and D of R&D. And typically now we should, it was earlier planned that we need to have marketing guidelines with us, which otherwise presently we are lacking. But now with two more components to it, that it should encompass social and commercial audit to it. And thank you for this insight. Thank you.
Thank you. It is a must. There have been many projects which have come out, products have come out, and because of the zero social acceptability, in spite of being a brilliant product, it has just failed. Just social.